Slide 1. The Ocean Environment, Unit 02A, Part 2, Pressure and Light. Slide 2. Light goes through water, but light is slowly absorbed by water until no more light is left. This is why the ocean gets darker and darker as one goes deeper into the ocean. On land, an animal can see another animal in the distance long before it can hear the other animal. Unless the animal is intentionally being loud. In the ocean, animals will hear other animals coming long before they can see them. Since light does not travel as well through water as it does through air, eyesight is less valuable in the ocean and good hearing is more important. Sound is transmitted much faster and better by solid objects. In other words, sound is absorbed less quickly by solids, so it goes farther before it is absorbed. Water is more solid than air, so sound travels faster and better in ocean water, making hearing more useful in the ocean than on land. For example, whale songs can travel thousands of miles in the ocean, allowing whales to communicate over vast distances. There are certain depths in the ocean where the water carries sound better, and the whales use these layers to their advantage. Sound can also be used to see underwater. Dolphins emit high-pitched noises, and then listen for the echoes that bounce off objects. This is called echolocation, and is how our sonar technology works. Dolphins listen for where the sound comes back from, its direction, and how long it takes for the sound to return. The farther away the object is, the longer it will take for the sound to return. Dolphins can not only determine the position of an object, but also tell what the object looks like, its shape. Slide 3. Pressure is, of course, caused when something presses or pushes against something else. In this class, we will primarily discuss atmospheric pressure and hydrostatic ocean pressure, which are caused by the weight of the air and ocean water above an object. The basic rule is this: the more stuff, air or water, there is above, the higher the pressure on things below it. More stuff is heavier than less stuff. More air is heavier than less air. When we are up in the mountains, there is less air above us, so the weight of the air is less and therefore the air pressure is lower. When at sea level, there is more air above us, so the weight of the air above us is greater and air pressure is higher. The atmosphere goes up pretty high. There is about 30 miles of air above our heads. We hardly notice the effects of the air pressure exerted by the atmosphere, because our bodies are built to tolerate it. It is normal for us. Water, of course, is much heavier than air. Every 10 meters, 33 feet, of water that is above your head is equivalent to the weight of the entire atmosphere. You really start to feel the water pressure, especially in your ears, when you dive towards the bottom of a pool, because there is more water above your head, so there is more weight pushing down, trying to push your eardrums into your skull. Note, sound waves are vibrations, fluctuations in pressure. Sound waves slightly increase or decrease the pressure caused by the weight of the air and water above ocean organisms. Many ocean animals can feel these vibrations all along their bodies, not just in their ears or similar organs, and use the information to find food and avoid predators. Slide 5. Atmospheric pressure can have a big impact on sea level. Changes in the weight of the air above the ocean can raise sea level by over 3 feet beneath storms. The winds of storms can push this mountain of water onto land, piling it up until it is over 20 feet above sea level and flooding miles of the coast. This is called storm surge and is how Hurricane Katrina overtopped the levees, pouring water into New Orleans, and how Superstorm Sandy did so much damage to New York and New Jersey. Slide 5. Atmospheric pressure can have a big impact on sea level. Changes in the weight of the air above the ocean can raise sea level by over 3 feet beneath storms. The winds of storms can push this mountain of water onto land, piling it up until it is over 20 feet above sea level and flooding miles of the coast. This is called storm surge and is how Hurricane Katrina overtopped the levees, pouring water into New Orleans, and how Superstorm Sandy did so much damage to New York and New Jersey. Slide 6. The ocean is pushed down strongly beneath the higher air pressure outside the storm, so the ocean rises where the downward push is weaker. The water that is pushed down has to go somewhere. This is somewhat like a seesaw or teeter-totter. If one end goes down, the other must come up. Examine the diagram showing the child, adult, and seesaw. The adult weighs more than the child, so they exert greater pressure on their side of the seesaw. The child's side rises even though the child is exerting downward pressure too. The child weighs less, so they exert less pressure on their side. Slide 7. Storm systems are associated with low atmospheric pressure, because the air in a storm system is warm, rising air. Warm air expands, gets bigger, so there is less air above each location, it has spread off to the side, and therefore less weight above each spot and thus less pressure above each spot within the storm. Slide 8. The color of an object depends upon both the atoms and molecules the object is made of and the kinds of light shining on it, the colors of the rays of light that are striking it. Sunlight includes all the colors of the rainbow: red, orange, yellow, green, blue, and purple. However, our eyes and brain only tell us about the strongest color of light coming from an object. We perceive the sun as being yellow, because the sun emits more yellow light than any other color, because more rays of yellow light come out of the sun than rays of red, orange, green, blue, or purple light. Other hot objects like fire and light bulbs also emit all the colors of the rainbow, and may emit more of some colors of light than others. Each substance absorbs some colors of light, and reflects other colors. The reflected rays of light bounce off the substance. As you can see from the picture below, we see the color of light that reflects off an object most strongly. In the picture, the person looking at the shirt perceives the shirt as being red because mainly red light is reflecting off the shirt while other colors of light like yellow and blue are being absorbed. The shirt looks red, because more red light is coming from it than any other color of light. Slide 9. The colors of light that are absorbed by an object make the object warmer. The energy in these colors of light is transformed into heat energy when the light is absorbed by the object. If no light is entering our eyes, we see the color black. You probably already know this, but it is easy to check. Just turn off all the lights, cover your head, or block your vision in some other way, and look around. This means that a black object does not reflect light. A black object absorbs all colors of light. If no color of light is much stronger than any other color of light, our eyes and brain tell us that the color of the object is white. In other words, a white object reflects all colors of light about the same. White light is a combination or mixture of all the colors of light. If one color of light is somewhat stronger than the others, then we perceive the object as having a light color. For example, a light blue shirt reflects all the colors of light pretty well, but the blue light a little better than the other ones. A pink shirt reflects all of the colors of light pretty well, but the red light a little better than the other ones. If only one color of light is reflected and only a little bit of it is reflected, then we perceive the object as having a dark color. A dark blue, navy blue, shirt absorbs all the colors of light well, but reflects a little blue light. A dark red, burgundy, shirt absorbs all the colors of light well, but reflects a little red light. Slide 10. Light on the red side of the rainbow is more likely to travel straight when it hits water molecules. Red light is the color of light most likely to travel straight when it hits water molecules. Light on the blue side of the rainbow is more likely to bounce off in a random direction when it hits water molecules. We call bouncing off in a random direction scattering. Blue light is the color of light that is most likely to scatter when it hits water molecules. The other colors of light are somewhere in between red and blue light. The closer a color of light is to red in the rainbow, the straighter it goes through water. The closer a color of light is to blue in the rainbow, the better it scatters. Slide 11. Light on the red side of the rainbow tends to be absorbed faster by ocean water. Red light is the color of light which is absorbed fastest by ocean water. This means that red light is absorbed quickly and thus does not go down very deep into the ocean before it completely disappears. Light on the blue side of the rainbow tends to be absorbed slower by ocean water. Blue light is the color of light which is absorbed slowest by ocean water. The other colors of light are somewhere in between red and blue light. The closer a color of light is to red in the rainbow, the faster it is absorbed. The closer a color of light is to blue in the rainbow, the slower it is absorbed, and the deeper it reaches before it is finally absorbed. Slide 12. We have learned that the color of an object or substance depends upon the strongest color of light we see coming from the object or substance. We have learned that blue light is the color of light which scatters most strongly in water and is absorbed slowest by water. Both of these contribute to the color of ocean water. If you are standing at the coast, blue light is the color which is most likely to hit the surface and bounce off, to scatter, and enter your eyes, so you see the color blue when you look at the ocean. You do not see the colors of light that go straight down. If you are beneath the surface of the ocean and look to the side, blue light is the color which is most likely to bounce off water molecules to the side, to scatter, and enter your eyes, so you see the color blue when you look to the side. Recall that red light tends to go straight, downwards in this case, so you will not see it if you look to the side. Because blue light scatters, blue light tends to take a pretty crazy path inside water. It scatters again and again and again. Slide 13. If you are far enough beneath the surface and look upwards, you also tend to see blue light. Recall that blue light is absorbed slower than any other color of light, while red is absorbed fastest. This means that red light dies out first, it is completely removed from the environment. Then orange disappears, since it is absorbed second fastest. Then yellow is removed, and then green. Blue light is the last color to be absorbed, the color that is left behind once all the others are gone. So, everything tends to look blue since it is the only color in the environment in a significant amount and thus the only color that can scatter off water molecules or underwater objects. Slide 14. I often oversimplify in this class. Now, I am going to add a little complexity. I'm not going to test you on this, but I thought some of you might be wondering, what about purple light? Purple light scatters more strongly than blue light and is absorbed slower. Why isn't the ocean purple? The sun sends a lot more blue light to the earth than purple light. So even though purple light scatters more strongly and is absorbed slower, there is so much more blue light to begin with that blue light typically dominates over purple. What about when the ocean looks green? What about other colors? If there are lots of phytoplankton, tiny algae, in the water, the ocean looks green, because phytoplankton are green due to the green chlorophyll inside them. Green sunlight reflects off their green bodies and out of the ocean. Like plants on land, phytoplankton use chlorophyll molecules to absorb and direct the energy to make food for themselves in the process we call photosynthesis. Note that some ocean algae use different colors of chlorophyll, colors other than green. There are red algae, golden algae, and brown algae. By the way, red tides are large groups of red-colored phytoplankton in the water. Sometimes ocean water is brown. This typically indicates that there are lots of sediments, like mud, drifting in the water. It can also be the dead bodies of lots of phytoplankton. If the water is shallow, the color of the ocean water may reflect the color of the ocean bottom. In other words, a muddy bottom makes the water look dark, and a sandy bottom makes the water look clearer. Of course, if this is the case, one is really seeing the color of the bottom, not the water. Slide 15. Notice that some ocean animals have a dark top or lighter colored underside. This is called counter-shading. Striking examples of counter-shading include orcas, killer whales, and penguins. Counter-shading helps predators who live near the surface of the ocean sneak up on their prey, and prey at the surface of the ocean avoid predators. If an animal looks down upon an animal with counter-shading, the dark top will look a lot like the dark water on either side and below it. The dark top will absorb the sunlight coming down, preventing it from being reflected upwards into the eyes of the animal looking downwards. If an animal looks up at an animal with counter-shading, the light-colored bottom looks something like the sunlight streaming down on either side of it. Its white belly does a good job of reflecting any light bouncing upwards off the water molecules and sending them back down, just like the light coming directly from the sun that is also heading down. Slide 16. You may have noticed that many deep-sea animals are red. Think of crabs, lobsters, and so on. What is so good about being red? There is very little sunlight in the deep ocean. At a depth of about 500 feet, 150 meters, only 1% of it remains, and sunlight is almost completely gone at 3,300 feet, 1,000 meters. Blue light penetrates deepest, because the other colors, especially red, are absorbed more quickly by the ocean water. Violet is absorbed more slowly than blue light, but there is so much more blue light to begin with that the blue light still dominates. Red is a great color for an animal to be if it lives far away from the surface, because little or no red light will penetrate deep enough to hit it. The red light will quickly be absorbed on the way down. Blue light that may penetrate down will be absorbed by its red body. Thus, any predators looking at the red animal will not see light coming from it, reflecting off of it. There is no red light to be reflected, and the blue light is absorbed, not reflected. Near the surface where there is some red light, the red light can reflect off the body of a red animal and into the eyes of a predator. Slide 17. Even though sunlight does not penetrate deeply into the ocean, the ability to see or at least sense light in some way is an important adaptation for deep-sea life, because most deep-sea animals are bioluminescent. They use chemicals to create light. A reddish body still helps an animal stay hidden, because almost all animals make blue and green light. Again, any predators looking at the red animal will not see light coming from it, reflecting off of it. There is no red light to be reflected, and the blue light and green light are absorbed, not reflected.